time of the day that's doing this. The other class did the laboratory, so we are not synchronized anymore. So let's take a look at what we're going to do instead. So tomorrow, you guys are going to do the laboratory. Those of you that, I'm sorry, we won't be able to do it tomorrow. Friday, you guys will be able to do the laboratory. Those of you that are coming in, they only had 2 for their class and they were able to handle it pretty well. Today, we want to then go over the solubility graph real quick. And then we're going to discuss something called molarity and work with basic molarity problems. And then tomorrow we will do dilution problems. And then next week, the tough stuff. So those of you who are coming in for tomorrow's laboratory, please make sure you read that through real good. That way you know what our expectations are. You're using pennies again. So unfortunately, this time we're not turning them gold and silver. You're using pennies in order to basically look at water droplets. So let's go ahead and get that solubility curve worksheet out and talk about it first. Am I on mute? Because nobody is saying anything. Are you guys just quiet today? All right, I will take that as a yes. You guys are all playing Owen's game. All right, so yesterday, last thing we talked about was eating hot wings and how the fats from this will meld with the capsaicin, and that will actually give you this. And then we talked about celery and carrots, and we had no idea what those were for. These are your utensils for eating blue cheese and ranch. You will look like a madman if you had a spoon and some blue cheese or ranch, and you're just sitting there shoveling blue cheese and ranch into your mouth. That looks pretty crazy, right? So that is the, what do we call it? The vessel for the blue cheese or the ranch. And that was it. That was what finished our miscible and immiscible discussion. And then what is actually meant by likes dissolving likes. Cool. So we can put this aside for a second. We'll get to molarity in a second. We want to go to what solubility curves are. Yesterday, I showed you a saturated solution, a supersaturated solution, and an unsaturated solution. We take a look. This right here these are the solubility curves for several different salts. Now, the old exercise was that you actually had to make this graph. So I didn't want to deal with that this year. So I got the graph off the internet. So keep that in mind. Usually you would have to make this graph, and that might actually help you. I don't know, by maybe not making it, you don't understand what all these lines mean. But basically, if we just let's pick 40 degrees Celsius. At 40 degrees Celsius, if we have 105 grams of sodium nitrate dissolved in 100 grams of water, we are at our solubility point. That is the maximum solubility, or that is the saturated solution of sodium nitrate. At 40 degrees Celsius, we'll have 105 grams of water. And 100 grams of water of that will be able to dissolve 105 grams of that salt. So let's try this one more time. At 40 degrees Celsius, we have a beaker of water, and that is 100 grams of water. We dump in some salt. How many grams of salt can we dissolve in there? 105 grams of sodium nitrate. At 40 degrees, how much potassium nitrate could you dissolve? 40 degrees potassium nitrate.
About like 65 grams.
65 grams, if we read this, 65 grams. So which one is more soluble at 40 degrees? Potassium nitrate or sodium nitrate?
Sodium nitrate.
Sodium nitrate is more soluble. We can dissolve more of that salt, right? Let's say we are at that point right here at 40 degrees and we have 105 grams. If we did this with all of these salts, which one would still be able to dissolve more? Which one would be unsaturated? If we took every single one of these salts and we put 105 grams and 100 grams of water at 40 degrees, which one would still make an unsaturated solution?
Potassium iodide.
Potassium iodide, because it's not saturated until we're way up wherever this is, right? So potassium iodide would be unsaturated. Sodium nitrate would be saturated. All the rest would be, if we were able to get them to dissolve, all the rest would be what?
Super saturated.
Super saturated. It's not likely that all of these would dissolve that much, but if we were able to do it, then they would be all super saturated. So let's take a look here. What is the solubility of KNO3 at 35 degrees Celsius? So take a second before blurting out the answer. 35 degrees Celsius, was it KNO3? 35 degrees Celsius, KNO3. What do you think? Maybe type it in. I don't use the chat enough. I'll open the chat. So type it in there. If you want, you can send it just to me. If you're worried it'll be wrong. Anybody want to say it verbally? No.
Is it 55?
Let's see. Sorry, I'm late. So that's fine. Yeah. Do you fall asleep in virtual study hall?
No, I was actually doing homework and then I looked at this and I was like, oh, I'm late to chemistry. My bad.
So if we take a look, here's 35 degrees and we want to do potassium nitrate. So we go right there. And yeah, that's probably about 55 degrees. I'm sorry, 55 grams. So the best way to write this would be 55 grams per 100 grams of water, because that's what you're doing. It's per 100 grams of water. For this, you could just put 55 grams and we'll just understand that this whole graph is per 100 grams of water. The problem is how much would it be if it were 200 grams of water at the same temperature? How much could we dissolve then?
Which is just 55 times 2, 110.
Right? And if we're 300, we would take 55 times
3.
3 and so on and so forth, right? That's just a little stoichiometry thing that we can do. If it were only 50 grams of water, then we would take that and divide it by 2. And yeah. All right. Look at this graph and find at least 2 that don't make sense. 2 that vary from most of them. At least 2.
Should we type it in the chat or just wait?
Yeah, do that. Type it in the chat. We'll give everybody a chance to look at it without just blurting answers out every 5 seconds. I'm not used to that either. But I think we can have that. Looking at all of them, 2 that don't make sense. Good, good. So if we take a look, a lot of people put SO2. So SO2, we see that as temperature increases, the solubility of it goes down. Not as much can be dissolved in water. Right? Why not? Why can't as much be dissolved in water? Anybody
Is it
want
a
to
gas?
think about SO2? Who said that?
Gabe.
Gabe. Very good, Gabe. Because it's a gas. Even if you didn't know SO2 chemically was a gas, like sulfur dioxide is a gas, you should be able to come up with the idea that, oh, that is weird. Why would, as we increase temperature, does it go down? And then pull from the knowledge yesterday. Remember, we said if we want to increase solubility of gases, we've got to decrease the temperature. We talked about fish deaths in the summertime. So it is a gas. I noticed that Owen put NaCl. NaCl just doesn't do what much?
Doesn't increase that.
It doesn't increase that much. It doesn't increase that much. The cool thing is too, is that it doesn't, if it doesn't increase that much, as we lower the temperature, it probably doesn't do what?
Decrease that much.
Decrease that much, which is a great thing, you know, to put it on roads and stuff like that. Because we still have, you know, it's still in solution, preventing that from freezing. So that's pretty cool. All right. I think that is enough to let you guys work on this. Please, if you do have questions on this, don't wait until Sunday and then try to email me. That's probably not going to be a good way to do it. Get the questions and ask me maybe Friday while they're setting up the lab, or even tomorrow if we have time.
Mr. Jackson, I have a question.
Yeah.
So when it says which substance is the most soluble overall, what do you mean? Are we supposed to look at like a specific temperature or just the graph? Why?
Look at the graph and basically you think from this information, which one is the most soluble out of these particular things at these temperatures.
Okay, so it's just like a general like trend. Which one is just okay?
You're welcome. Yep. All right. There was one question that, oh, let's do one more thing. This is a good one. So let's say that we start at 60. Let me just pick something that's, where does this intersect best? Right here. 60 degrees. We start at 60 degrees and we're dealing with a sodium nitrate again. So I'm at 60 degrees, about 125 grams can be dissolved at 60 degrees, right? 125, is that, am I reading that right? 60 degrees, 125. 125 grams dissolved of Na sodium nitrate at 60 degrees. Let's say I cool that to half that temperature, 30 degrees. So what's going to happen to all of this that's dissolved if it's not forming a saturated, supersaturated solution? All of this
So
to do what on the bottom?
will they precipitate at the bottom?
Yeah, it'll precipitate. Basically, it'll form that solid at the bottom, right? So how many grams would I expect to find at the bottom at 30 degrees? Well, we know that 95 grams will still dissolve. So what is the difference between 95 and 125?
30.
30. So that means that 30 grams will fall out of solution or deposit or precipitate. Hopefully I didn't answer the question. No, I didn't. But if you take a look, there's a very similar question here at 14. It says, what would fall out of the solution? That's what they're asking. It's a pretty specific one. All right. Are we good? What's Sunday on that? All right. Bring in molarity. Now, as you guys have been in here long enough. You know that these are set up so that you could sit here and go line 1, line 2, line 3, and it's set up like a textbook. You should be able to read through this and figure out molarity. I'm not going to do that. I'm not going to read with you. I'm just going to give you the concepts and then show you how I try to solve these problems, just like always. So we have some definitions. Hopefully you know these by now. Solvent, solute. This is what's dissolved. This is what does the dissolving. Or if you're chemistry, then you would say which is in larger quantity and which is considered in the smaller quantity. Now, molarity, basically the most important thing in chemistry is going to be the mole, probably for you guys, right? For this course, the mole is everything. That's the stuff we did last year. It correlates with the balanced equation. Well, we're going to find that the mole correlates with solutions as well. So molarity, and maybe I shouldn't just show this out. Let's do a few other ones before we do this. Molarity is basically just a concentration for chemists. Somebody tell me what a concentration is. When I think really hard on my homework. No.
Like how much stuff is in something, like compared to?
Louder?
Is it like how much stuff is in something like?
Yeah. Those solubilities were actually concentrations. They were grams per 100 grams of water, right? That's what that graph showed you. How about anybody ever drink orange juice? Yeah, what does it say on there? Made from?
Like 100% juice or 100%?
I hope so. You're drinking the good stuff, actually. Not everybody can drink that fresh squeeze stuff. What does most of our orange juices say? Somebody run to their louder.
90% juice.
Okay, go grab some orange juice. Somebody that has it and look at the bottom or look on it and find what it says on there for us if you can't think of it.
Made from Florida oranges.
Yeah, but what more? Read more.
From concentrate.
There we go. Made from concentrate. So basically, the way they make orange juice is the orange juice that they're making is like a percentage of new oranges and a percentage of old oranges. Basically, what they're doing is they want the orange juice to stay the same flavor. They don't want a sudden change just because the crop changed, right? So, I mean, that's very important. I mean, it's like, what if you went to a McDonald's and ordered a hamburger and all of a sudden it tasted like a Burger King flame broiled burger? You might be like, well, this is garbage, right? So like Tropicana and stuff, they don't want their flavor of orange juice to change. So if they have surplus of crops some years, they will sit there and concentrate this, basically get all the water out and then freeze the stuff, right? And that way they can mix that in with next year's batch and so on and so forth, so that they get a consistent flavor. It's a continually happening. Otherwise, you might get, I mean, have you ever bitten into an orange and you were like, this isn't a good orange, I'm going to toss this? Imagine if one year that's all the oranges they got, and then like, where'd the orange juice market go? Nobody's drinking orange juice anymore, right? So that's made from concentrate. Basically, they have something and they add water to it. That's basically what concentration is. How much of a thing compared or per total sometimes, or another thing. You might get something like percent by mass. Percent by mass is another concentrate. So we have the total mass of this, and we know the mass of, let's say, the drug that's in there. Let's say there's a drug. This drug is a caffeine pill. So it is 5% by mass. That means you may take the whole pill, but like if the pill weighed 1 gram, 5% of 1 gram would be how much is actually caffeine. I think yesterday, did we bring up the idea of daiquiris and how water and alcohol can mix? They're miscible. So if you look at these spirits, a lot of times they're called spirits. Well, they measure the amount of alcohol by something called proof, right? And if it is 100 proof, then that means it will catch fire. That used to be the way that, like, if you ever play Red Dead Redemption or any of those games, that used to be the way that they would sit there and tell whether or not the bootleggers or the people that were making alcohol, whether or not it was true stuff. You could sit there and hold a match up to it and it would light, like a lit matchup to it, and it would actually catch on fire. That gave you 100 proof, right? Well, today 100 proof actually means that it's 50% alcohol by volume. So you take the proof, you divide it by half, and that tells you the percentage of alcohol. For example, a lot of things like vodka, tequila, and these other liqueurs, they are 80 proof. That means that they're 40% alcohol by volume. Now, there is a big difference of drinking a glass of, something that's 50% alcohol by volume and something that's 40% alcohol by volume. You guys probably learned about that in your health class, right? One shot, which is 1.5 ounces, is equal to 1 glass of wine. Did they teach you this in health class? No. 1 glass of wine, which is equal to 8 ounces, right? Leo's turning on his camera for this good stuff. No. One
No,
shot.
sorry.
No,
Never mind. I'll tell you.
no, I like that picture behind you. So one shot is 1.5 ounces. That's like 40% alcohol by volume, that one shot. 1 glass of wine is about 6 to 8 ounces. That's usually about 10% alcohol by volume. The average beer is usually 12 ounces, which is 4 to 5% alcohol by volume. So the actual way that these are distributed is based off of their percent alcohol by volume. Each of these you should only have, and you guys should have none of it, because Indiana state law says that you guys should not be able to drink until you're 21. But each of these, for responsible adults, they should only have one of these beverages per hour, because that's how long it takes for your liver to process that alcohol. So that's why one shot is so much smaller than a glass of wine, than a beer, right? And beer is the smallest because, beer is the largest because it has the smallest alcohol content, 4.5% alcohol by volume versus 40% alcohol by volume, right? Huge, huge difference. So those are another concentrations. We could do concentrations all day, to tell you the truth. There's so many different ways to do it. But for chemists, this is the way. You can always find the moles of any substance because you can find the grams of any substance. And by knowing the mass, the molar mass from the periodic table can get you to moles, right? Liters of solution. Now, this is the most important part of this. This is after you've added in your moles of solute. If you sit there and you have 100 milliliters of solution and then you dump some solid in there, what's going to happen to your volume?
It goes up, it increases.
Yeah, it's going to go up, right? So you maybe start off with half of the substance that you want to, the solution that you want in the end. You dump in your solute, and then you take the volume up to that. That will give you a more accurate molarity. So all molarity is you find the moles and you divide it by the liters. That's it. So let's say, calculate the molarity of a solution made by adding, they don't even make it nice for you. Let's do this first. Let's say I have 2 moles and I put it in 500 milliliters. I have 2 moles of something, let's just say NaCl, and I put it in 500 milliliters. Do I have a molarity here? I need to get molarity, I need moles per liters. So what do I need to do to 500 milliliters?
Divide by 1,000.
We don't talk like that in here, right? We use the step process.
Yeah.
So what goes on top?
Oh, 1,000. Wait. Wait.
Making it hard. What goes on top has to cancel out the milliliters, right? So 1,000 milliliters goes on top, and that is equal to 1 liter. So you want to divide this. You could have also just put the decimal over, right? And change this to 0.5 liters. But yeah, if you're doing this method, remember, make sure those cancel out. So we get 2,000 divided by 5. I'm sorry, yeah, 2,000 divided by 5. Oh, I'm sorry, 500. 2,000, come on, man. What's going on here? What's this function? How do I escape this? Oh, quit. There we go. 2,000 divided by 500. 4 moles per liter. And I only used one significant digit, so we're going to keep it at that. We would say that that is 4 molar, right? If you did the conversion in your head, you would have gotten the same thing, right? 2 divided by 0.5. I just want to make sure that we can get back to this because it seems like it's been so long since we've used this type of math. And that's going to make this hard for you. Hopefully the teachers from last semester over there, hopefully, I feel like I call them over there, the ones over there, hopefully they use the same methods that I'm showing you. We call this dimensional analysis. It is the key to most chemistry. If you haven't learned this yet, you're going to struggle. It makes everything easier. I promise. I promise. So concentration is moles per liter. Let's try this one now. We have 141.7 grams of nitric acid, and we add enough water. See, this is how you use sneaky language to make sure that you understand that we're not adding it to 750 milliliters of solution. We add enough water to make that much solution. So that is the liters of solution. We want moles per liter. So out of these two, which one can get me moles? 141 or 750?
141.
Why?
Because it's in grams, you can convert that using the molar mass.
Good. Another quick thing that we did last semester, just to make sure that we remember. If I want 2 units here, moles per liter, I start my math over here with 2 units. So I'm going to have grams per milliliter. I need to change both of these, right? Good thing I have white out because I don't know if I have enough room to do it. I'm going to go ahead and change these liters first, just because I don't have to do any thinking to change those liters. That right there is almost like muscle memory for my brain. Milliliters, 1,000 milliliters is 1 liter. Boom, boom. Right? Now I've got to do a little bit of thinking. This is grams of nitric acid. So that's going to be 1.01 for the hydrogen, 14.01 for the nitrogen. What's 3 times 16? Let's see, 32, 48, 48. 48.00 for the oxygen. Where did these numbers come from?
Periodic table.
Periodic table, correct. Right? So you're going to need your periodic table. Anytime we go from grams to moles, you need periodic table. What number is going down on the bottom here? Is it grams or moles?
Grams.
Grams. That's 63.02 grams. And that's equal to what? We call it the molar mass for the reason because it's the mass of how many?
1 mole.
1 mole. Bada bing, bada boom. If it's on top, we multiply. If it's on bottom, we divide. Welcome back, math. Some of you might be excited. Some of you might be like, oh, I loved making things with marshmallows. Can't we just do that all the time? And hopefully you got 2 point, how many significant digits? Oh, 4. This is weird. 2.998 is what I got. 2.998. That's a lot of significant digits. You can, I'm going to rewrite that because I got some scrabblies like through it. You can rewrite that as moles per liter or molar. If I want to talk about this solution, instead of saying, well, it has 2.998 moles per liter of nitric acid, I can say it's 2.998 molar nitric acid. Which one took less time to say? It has 2.998 moles per liter of nitric acid to water, or it's 2.998 molar nitric acid. That's what that means. That means the same thing. If I say that's that molar, that's what it means. Why are they off by 1? 63.01 They probably called nitrogen 14 instead of 14.01.
I think they also rounded the moles off.
Ah, yeah, right. Again, I'm not a big huge stickler for this, but if you do that, then you need to see if this is a multiple choice thing. You need to be able to see that it should be that, right? I did no rounding until the very end here. One time rounding is what we are striving for. Go ahead, I'll give you a few seconds to try this on your own. Yeah, I think I've seen this band almost more times than any other band. But I've seen 500 several times. I think they're almost tied with other than that. But yeah, I love them. All right. .42 grams rubidium chloride. What's funny? They gave it to you. Sometimes they'll just give you the word. I mean, you got to sit there and go +1, -1. Because if you mess this up, guess what you can't get? Can't get the molar mass right? I do want moles per liter, so I need to start with two things. So I'm going to start with 2.42 grams on top and 250 milliliters on bottom. Again, if you're like, that's stupid, why waste the time? By all means, you can change that in your head. I'm just doing this to show you, to make sure everybody's on the same page. Some people are quicker and they're like, that, come on, dude, that's 0.25 liters. Some people are not. So since we're in the learning mode right now, it's best that we do it that way. That way everybody can stay with us. If it's on bottom, we divide, and if it's on top, we multiply. Sorry, I just had a piece of candy and I think that my body is reacting to it. Did you guys get 0.08? If you got 0.08, you're wrong. Because what should it be?
2 sig figs.
Yes, actually, it should be 2 sig figs. Based off the 250. So 0.080. Right? We're just getting back into that math game, right? So we have to keep in mind all of those silly things. All right. So one of the things that I've said is that if you want 2 units, you need to start with 2 units. And this becomes huge right now. So we see a chemist wishes to prepare 0.500 liters of an 8.0 molar aqueous solution of sodium hydroxide. How many grams of sodium hydroxide should she use? This is the most common practiced problem for this unit. Because a lot of times, how are you going to know? Like, most people know this. I'm going to grab a handful of rubidium chloride, 2.42 grams, and I'm going to dump it in 250 milliliters. And then I want to find the molarity of that solution. That's not usually what you do as a chemist. You sit there and say, well, I need to make a solution that is 8 molar, and I'm going to need 300 milliliters of it. So I'm going to go ahead and make 500 milliliters or 0.5 liters of it. This is more common that you would do than this. This tells you what molarity is, but actually working in a laboratory or something like that, this is more common. And this is the funny part. And I'm not being mean to any biology teachers or anything, but biology teachers come down and ask how to do this all the time because they read in a laboratory that they need a particular solution of, they need a particular amount of a solution. So one, they're trying to do this usually for 30 kids in a classroom. So they need a lot of it. And two, they haven't done this type of math since at least college, maybe, which could have been, you know, several years before. Usually I just make it for them and then I write on there like how to do it for the next time. Put this many of this and this. And it's not a hard thing. It's just that whenever you haven't done it for a long time, you sit here and you look at this and you're like, what? So let's do it. How many grams? How many units does that have?
1 unit.
1 unit. Does everybody understand what that means? It's not moles per liter. It's just grams. That's what I want. That's one thing. It's just grams. It's a mass. This is moles per liter. That's number of particles per volume. That's 2 units. So I want grams. Which one of these has 1 unit? Liters or molar?
Liters.
Right? Molar is still, even though it looks like 1 letter, it's still moles per liter. So liters has 1 unit. So that's what I want to start with. Now I got to get rid of liters. How am I going to get rid of liters? Well, what did I say? 8.0 is actually moles per 1 liter. Isn't that what molar means? So am I going to put it in this way or am I going to flip it?
Keep it that way.
Yeah, right. If I have liters here, liters has to go on bottom. And to tell you the truth, I don't usually write this out. So what you're going to hear me say instead is that for every 1 liter, there are 8.0 moles. That's what that means. Am I done? Liters canceled out and I have moles. I'm not done because I want grams. They gave me the molar mass for this. It's probably not right. Hey, it is right. So we have every 1 mole this time goes on bottom. Why does it go on bottom? Because I have moles on top is equal to 40.0 grams. .5 times 8 times 40.0. I haven't used it in so long. 160. 160 grams. What do you think? What are we going to do down here differently? What do we have to change first?
Milliliters to liters.
So 275 milliliters every 1,000 milliliters. Again, you can change it in your head if you want. Is 1 liter, and every 1 liter has 2.00 moles, and every 1 mole is 40.0 grams. Again, to people who didn't get this a long time ago, this is going to look atrocious, but this is by far the best way to solve these problems. If you don't do it this way, you're going to have to sit here and say, okay, molarity equals moles per liter. So I need to get liters. So I can't even do it. It's so hard for me to put my mind back into this mode of problem solving. Moles per liter, right? So what is the molarity? It is 2.00 molar. What is the liters? Well, I got to change that to 0.275 liters, and that will give me X. So 2 times, yeah, that's right. 2 times 0.275.
It's 0.55.
So that's 0.55 moles. And what is, will I be able to do this? Yeah. what is the formula for it? Mass divided by moles equals molar mass, right? Mass divided by moles, grams per mole, right? Mass divided by moles equals molar mass. So if that's our formula, then we would sit there and we have moles, we have molar mass. So we're going to rearrange that to take the moles times the molar mass, which is 40. 0.55 times 40.
It's 22.
Right? Now, I did so much thinking there. It actually almost broke my brain several times. With this, I see milliliters. I am milliliters per liter, liters per mole, moles per grams. 275 divided by 1,000 times 2 times 40.
It's 22.
Is it 22?
Should it be 22.036?
22.0. Stinking significant digits are back, right? That's why this has those problems like that, so that it reminds us again of what significant digits are. And it's been so long. I heard somebody in the lab today go, I thought the 0 before the decimal place wasn't significant. And I was like, that is true. The 0 before the decimal place is not significant. So people are forgetting those rules, right? And this diluting a stock solution, that's actually what we're saving for next time. So if we take a look here, these practice problems on number 4, I would do these 4 for this evening. I will put the answers up by tomorrow. I've got a lot of answers I need to put up today, I think. So I'll put those answers up by tomorrow. If you have questions, by all means, stick around. Otherwise, you guys are free to go and have a great day. And I'll see you guys tomorrow for a shortened period. Hopefully you guys aren't stressed out too much about your personal projects. Remember, you don't have to present them, but you do have to have everything given to your teacher by tomorrow. Bye.
Mr. Jackson,
Yeah.
yesterday my Zoom wasn't allowing me to join it, and I joined the Zoom late.
Oh, okay. So I need to mark you present.
I joined. Well, I joined late.
Oh,
Just
what are you
rewatched.
asking? Did you watch the video? I don't know what you're asking me, Uriah. Do you need help or something, or is this an attendance problem? I think you're on mute, buddy. I can't hear you.
I think it cut out. I couldn't hear anything.
Oh, okay. So is this an attendance issue, or what are you asking me? Do you need help on something?
When was the lab started? Did you start the lab yesterday?
No, the lab is going to be for this class. The lab is going to be Friday.
Okay. Thank you.
You're welcome.
You can go first, Brody.
I think you can go first. I have questions from a few days ago, so it might be easier.
Okay. We have English. We have the same period, next period anyway. So it's really I'm not even asking about chemistry. It's just the reason my camera was off. It's sometimes it works. Yeah, it's like
I'll tell you what. I actually have problems with the class one with that. So I get you.
yeah.
Yep.
Yeah, like I'll click it, I'll turn it on, and then my entire screen will go like black, and I don't see anything, and I have to leave the Zoom and come back in. And then today I tried it, and I was just like laying on my bed because my camera doesn't work. I can lay on my bed, and then it turned on. And I was like, oh, okay, I guess. But yeah, okay, thank you.
No worries at all.
Have a good
Yep. I'm not a stickler about it at all. I was joking whenever I was like, oh, is this how we're playing today?
Have a good day.
You too, Leo.
All right, I actually have a question about like the first pack you gave us like at the beginning of the week, I guess, like at the end of last week.
Oh yeah.
Like just like some of the problems.
Yeah, let's take a look. You mean with intermolecular forces?
Yeah.
All right. So like 11 and on or something?
Yeah, actually, yeah.
Yeah. If they're very volatile, they're going to be weak because they can't hold on to each other.
Mm-hmm.
Can you see these?
Yeah.
If it has a very high boiling point, that means they hold on together real well. They're going to be strong. Vapor pressure is the pressure that's needed to be on top of them to keep them in liquid and gas equilibrium. So if there doesn't need to be much on top, that means they are holding each other very well. So that would be strong. Very viscous. Viscous stuff is like slobber of a baby. You know how slobber of a baby just sits there and like holds on to itself and slowly goes down and down and down.
Yeah.
That means it's holding on to itself very well because it's very viscous, and very high surface tension means that it's holding on to itself as well.
Oh yeah, that makes sense. No, I guess the questions I had were over 1 and 2.
All right. So when we're
like I could do some of them, but some of them I just couldn't do.
all right. So basically you're looking for nothing, which is London dispersion forces, polarness, which is dipole. So this is nothing. Everything gets that. Dipole, you got to have polarity. It's got to be a polar molecule. And then hydrogen bonding, it has to have polarness. It will, and it has to have some hydrogen bonded to a NOF, either a nitrogen, oxygen, or fluorine. So here we have nothing. So that's London dispersion. Here we've got polar. So that's dipole.
So do we just know it's how do we know that's polar?
We know it's polar because you would have to do.
Is that because like the chlorine and the hydrogen are like 0.9?
No, it's based on the carbon. So you have to draw the actual structure out.
Okay.
And if we look at that, carbon is 2.5 and chlorine is 0.3. So the electronegativity difference is 0.5, which is polar. And that's going to pull the electrons toward the chlorine.
All right.
Yep. So here, this is going to be polar. So it's going to have dipole up. I almost passed it up. Since this nitrogen is attached to this hydrogen, what else does it have?
It has hydrogen bonding.
Yeah, right.
But since the hydrogen bonding is a strong, okay, yeah.
Yeah, we're just looking for the strongest, right? Here, this is an ether, so these oxygens are not attached to hydrogen. So this is only dipole. Right? H2O, definitely hydrogen bonding. CO2, London dispersion. Alcohol, hydrogen bonding. AR, that's nothing, London dispersion. A PF5, that's not even going to have dipole. It's just going to be London dispersion. And PF3, I've got to draw this one out because I don't know. So if we take a look, 21 plus 5, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So that's trigonopyramidal. The electronegativity difference between fluorine and phosphorus is 1.9. So that is definitely dipole.
Okay. That actually makes a lot more sense.
Yeah, I mean, it's based on, this is all it's based on. You find these out, then you get it, right?
Okay, yeah, that makes, that's a lot more clear.
Cool.
Well, thank you.
You're welcome. Have a great day.
You too.